Alright, time for another draftphysics.com, debatephysics.com, also video presentation. Yeah, okay. I thought I would do a video just devoted to the drag argument, related basically to Lesage gravity, which is really photiogravity, which, again, it should be understood that Newton actually liked as a theory, and he didn't really comment on it much, but he did like Fatio, and there was communication and blah blah blah. So anyway, it's just the idea of a particle force type gravity. The idea is there's ultra-mundane particles in the universe. They have motion, they collide with objects, and they end up creating this shadow effect on each other. And the shadow means a lack of force gets through the object, so the other object gets hit more from one side than the other. Now, Richard Feynman describes this in a video, one of his famous lectures, and he uses drag as the disqualification. So I'm explaining why that disqualification isn't really a disqualification. All right, because nobody really thought about it, and that's the funny part. Nobody simulated it, nobody... You can draw it, but I mean, it is a little hard to keep account of it. I mean, it would be best to do a mathematical simulation, a visual simulation based on the simple mathematical constructions of the rules, which is you have these little discrete bits, and that some percentage of them are going to be absorbed by an object when they go through the object, and the fact is some of the momentum is going to be absorbed, and therefore it won't get to the other side to equally push, and it'll make the object move. So in this simple example, the argument is everything is sitting in space, and it's being bombarded by, theoretically, the same amount of force from both sides. Now, I'd say obviously that we're not, because we're in all this gravity, we're getting pushed all over the place, but anyway, so we're never balanced. But the point is that you wouldn't move. You would just jitter in place as this equal amounts of force hit you. And so for the drag argument, you're basically saying, well, if you're moved into a force, it would end up slowing you down. That is, if I did plow into the force in one direction, it would absorb my momentum, I would stop, and that's the end. And the catch is, it's not the end, and you won't stop, because you really can't evade the force. You can just change when you hit it, and that's the key difference. So if I added one more bit of force to one side, then it's going to get a bias. It's going to move into this opposing force, and it's going to what? It's going to hit it sooner than it would have. So a force bit that's, say, this far away from me, if I'm moving, I'm going to hit it before it would have hit me, right? It would have come in, hit me, and left, or got absorbed. And instead, it's going to get reflected because I'm going against it anyway, but whatever. The point is all that changes is now I hit it sooner here, before it got here. That's all it's going to change. I hit it sooner. I can't change that I will hit it, and that's the key point to raise, is that all that can happen is yes, I'll hit this opposing force sooner. That will be essentially the same as being hit by more force. It will, in fact, stop the object. Okay, the object's going to be here. So we gave it momentum here. So we gave it a little bit of momentum. One extra little force bit spread over the giant mass, gave it a little momentum. It moved into this opposing force, and it did, in fact, we'll just put an X for stop. It did, in fact, stop it. But all of this force is still in the environment. I mean, what you did is, not only did you plow into a force, but you evaded a force. So if there's force coming this way, and I move this way, well, then that force hits me later, right? So all I'm doing really is hitting one force sooner and one force later. So all of this does catch up, and so I'm still going to get hit. I got hit by that, And now I'm still going to get hit with this quantity, which means I still have that 4, okay, instead of the 3. And the fact is that's going to start me again. So I'm going to get pushed forward again. I'm going to be given momentum again. And then the same thing's going to happen. I'm going to stop. And then the stuff's going to catch up. I'm going to get pushed forward again. Because I can't get rid of this extra one I put in here. It can't go away. The simple fact it's on that side. There's no way I can change how much is on that side of me. The amount of force on that side of me can't get changed by this process, by me moving. Me moving doesn't change how much stuff is on that side of me versus how much stuff is on that side of me. In the end, I have to interact with all of this stuff. So no matter what I drew as the parameters of the time and the motion, the container I'm going to make for this, it doesn't matter. What's on this side and what's on that side has to remain the same. So if I introduce a new bit of force on one side, it's permanent until somebody introduces another bit of force coming the other way. So until an opposing force, somebody shoots a laser beam, hits the matter is going to keep moving until somebody shoots a laser beam from the other direction, compensating for the fact that you added energy to that side. That side keeps the energy. It can't lose the energy. It's still always going to be there because you had 3. You used 1 to jump ahead of the 3. The 3 are still going to show up. You plowed into force sooner on the other side, but you used up 2 to stop, and there's only 2 left. You have 3 on this side and only 2 left on that side. Therefore, ergo, you're going to be continuing to go. So basically something's motion in the real physical space is it goes, it stops, it goes, it stops, it goes, it stops, it goes. That's what's really happening when something's continually moving in space. So when you throw something into space, a wrench is, I throw it and it keeps going forever. It keeps going forever in this manner. It's going forever, but it is actually being dragged. It is actually plowing into more force, but it's also only more force in a moment of time. It's not more force absolutely. There's not more stuff on one side of the universe than the other side of the universe. The wrench can't change what it's going to hit. It can only change when it's going to hit it. And they could, like I said, this is easy to simulate on a computer, but if you've got some kind of intuitive engineering skills, you can figure out pretty quickly that, if I add up how many times it gets hit, if I just simulating the hits and give the same motion to an object per hit, like a go, a stop, a go, I can't change. If I introduce a force, a bit of force, it's permanent until I introduce an extra bit on the other side to compensate. There's no automatic compensation. You must add an extra bit of force for there to be a true stopping force. You can only temporarily stop it. So again, I'll just emphasize again, you can't change how much force is going to hit you as you plow into the force. You can only change when it's going to hit you. And we're talking about stuff that happens over trillionths of a second. So the when is pretty irrelevant. Alright, so I'll now play the Flyman video clip where he's describing the Lesage gravity, which again, I'm not arguing exactly for that, but pretty close to it. But what I'm clearly saying is that yes, the drag problem isn't really a problem, and therefore the model that does fit in every respect is now safe from critique, okay, as having errors or catastrophic failures, because the only one that meant anything was the drag issue. They used to bring up heat, and there's a great irony in bringing up heat that somehow a physical gravity force would create heat. And yes, the irony is that the sun is burning hot. A pretty good demonstration that gravity creates heat. The Earth is molten in the center. And physics doesn't give you a really good explanation for that. I don't know if there's some, I wish I had an audience so I could say, hey, has any of you people heard any physics explanation for why the center of the Earth is molten? Why most of the Earth is in some liquid state? And, very hot. And, the only explanation I've heard is something like, well, 4 billion years ago it got hit by meteors. Well, how did it hold the heat for 4 billion years? I mean, there's no concept of insulation here. I mean, there is no perfect insulator. Even empty space can't stop radiant heat, photons. So you're going to dissipate your temperature. Nothing can just hold its temperature. You give it a temperature, you don't give it any more energy, and it just holds that temperature forever. That can't happen. So it's kind of silly, to argue that the Earth got hot 4 billion years ago, and no new energy has been put in, and it just stayed hot. That's nonsense. It's hot because it is exactly doing this. It's all the little matter bits are pushing on each other. Tons of momentum is being exchanged, and in that process, a lot of heat is being dissipated. A lot of motion, a lot of MV is being converted into very small things moving very fast. All right, so I think that's enough of a premise and enough of an explanation. I think, obviously I want to talk to people who know something about physics, so this isn't for people who don't know anything about the physics or the history. But the Feynman clip will speak for itself. It's a decisive argument in the sense that this has been used by physics to evade, real models of force. They discount all these real models of force based on this Feynman argument. So it should be understood that, once that argument's defeated, they really don't have an argument against it. And it really is simple, and it's mechanical, physical, and it works. Yeah, really well as an explanation, as a model. All right, so leave this pause and move on. All right, I'm back. So let's see. Hopefully the volume will be adequate and such.
He says it tells you how it moves. It should be enough. I told you how it moves, not what.
Okay, so he's talking about Newton, and Newton's basically just gives you this formula that says this is what it does. Now, really, Galileo gave us the formula in the sense that Galileo measured the 16 feet in 1 second that something falls, and that's the 9.8 meters per second, which is all you really need to know. But anyway, moving on. I mean, this idea of combining the gravitational force of the moon and the Earth and doing a calculation of the total amount of force between the two objects in terms of the opposite directions isn't all that valuable, frankly, in most cases.
But people are often unsatisfied without a mechanism, and I would like to describe one theory which has been invented among others, of the type that you might want, that this is the result of large numbers. And that's why it's mathematical. And
So this was invented in the 1600s by a guy named Fadio something or other, Fadio. He got discounted because he was a part of some cult or something, and some sort of bad reputation in the end. He actually was the one who incited the argument between Leibniz and Newton over the calculus. So he was a player, it's just that he's sort of been written out of history. And it was basically his suggestion that you could understand the mechanism of gravity as just this idea of absorbing the substance of a force coming in from all directions, and that more goes in than comes out, essentially, and therefore stuff on the outside of that thing will be pulled in because the thing absorbed the force that would have hit them. And what it really does is absorb time. Again, it's just a time argument. The force doesn't get to you in the same time. And that's the difference. But leave us continue.
I give this theory, perhaps you've thought of it yourself. Every once in a while some student comes running in, he suddenly explains gravitation.
Yeah, so that's it. I mean, I did the same thing. So without ever knowing who the word Lesage and without ever hearing a Fadio, I did exactly the same thing. I said, well, look, there's these photons flying in at the speed of light. What if some portion of their energy is absorbed and therefore there's less energy coming out than went in? And that's what the heat is. The heat has to be constantly fueled. There's no wood to burn. So the fire essentially has to be constantly fueled by something. And what it's being fueled by is the momentum of that force. The force loses its momentum trying to get through the earth, and the momentum is used, let's put it that way, to move matter. And moving matter moves slower than the force, so therefore the force doesn't get where it was going as quickly. Alright, continuing again.
Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, shooting by.
So this is a suppose that we know is an absolute fact. So you already know that there is a ton of stuff going through you, forces. The magnetic field of the earth is going through you, cell phone calls, all kinds of stuff. There's all kinds of stuff we know that moves the speed of light that's going through us. And they kind of know that gravity moves at the same speed, which is the irony of this conversation. Because they will concede that if the sun disappeared, it would be 8 minutes before the earth would change its motion. Because it doesn't know the sun disappeared. It'll take 8 minutes at the speed of light for us to feel the change. Because it is a real force. This is just so ironic that he would talk about this idea of a bunch of energy in the universe when that's exactly the truth. We already know there's a bunch of energy in the universe. You're not going to get a suntan from it, but it's not 0 degrees Kelvin out there. There's stuff hitting you all the time. There's no place to go where there's no starlight, so to speak.
Shooting by, and once in a while hit us in a bombardment. But we and the sun are practically transparent for them, nearly. But some hit, and so it's not completely transparent.
So the transparent argument doesn't need to be too complete. The idea is just that obviously you're saying there's an amount that's the total amount of force. And if you consumed all of it, then no force would come out the other side, and you'd have whatever the maximum value is of the energy of the universe, in the sense of the absolute pressure. And you could argue that that might be the limitation. That's why the suns only get so big and they don't get any bigger, is the fact that, yeah, you used up all the gravity, you used up all the energy to maintain the pressure, to keep the sun's pressure high enough to stop it from blowing up. And so the containing pressure stops increasing as the size increases, and therefore the center, you could argue, would get cold because there wouldn't be any capacity to increase the pressure. But anyway, that that is speculation. We don't need to go that far.
Then look what would happen. If the sun is here and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang bang, the few that hit, which would not shake the earth in any particular direction, because there is many coming from one side as the other, from top, from bottom. However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun and don't go through. Therefore,
So, okay, hit the sun and don't go through. We know that, well, if they hit something, they exchange momentum. We can't destroy the momentum. We can't, as Descartes would say, we can't stop the flow of the energy. It's always going somewhere. It's always somewhere. We can always find it. That's one of Feynman's own arguments, is that this conservation of energy really means these are real blocks, these are real things, and you can just say the energy exists here, and then this thing stops and that thing's moving, so the energy got exchanged, and that's the simple explanation. It's a physical exchange.
the number that are coming from this direction toward the Earth is less than the number that are coming from the other side.
So that's the simple argument, that obviously you changed how much force is hitting the object because you put something opaque in front. You stop the wind, so to speak. You block the wind going towards you, and then there's still wind behind you, so you're just going to get pushed into the thing that blocked the wind.
Because here they have no opposition from no sun there. And it's easy to see after some mental effort.
So that it would obey perfectly the inverse square law, and obviously the little shadow that the small object produces would be, proportional, in terms of, what something else is going to perceive, as the big object. So it fits Newton's equivalence between the forces. The small mass can only acquire so much motion from the change in the field, and the big giant mass can obviously only be moved very slowly. So one object can move fast, but there's very little mass. One object is humongous, but it can only move very slow. But the amount of movement in the two objects will be, the total amount of their momentum change will be the same.
That the further the sun is away, the less in proportion of all of the particles are being taken out of the possible directions in which particles can come. I mean, the solar size appears smaller. And in fact...
All right, so the inverse square law is just the idea that something spreads in two directions. So it's the same as a light bulb. The photons leave the light bulb in little rays. The little rays are separating this way and this way. So the canvas that the photons are falling on is getting 4 times bigger for twice the distance. So I go 2 units of distance, I made my canvas 4 times the size. And so obviously the photons get dimmer and dimmer because they have to spread over a much larger surface.
Inversely is the square of the distance. So there will therefore be an impulse toward the sun on the Earth that's inversely as the square of the distance, and is the result of large numbers of very simple operations.
Right, so very simple physics, a very simple mechanical process. This makes a ton of sense. We already know the photons exist. Clearly there could be photons we can't tune in with our receivers, right? We're totally frequency dependent. We only can interact based on something having a specific frequency. Well, what if it's pieces of stuff? Instead of ... it's just ... That kind of simple argument. So there could be a ton of broken pieces of energy in the universe, broken photons, and we wouldn't have any way to detect them, except as gravity. Except as there's the obvious detector, gravity.
Just hit one after the other from all directions. And therefore the strangeness of the mathematical relation will be very much reduced because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating.
So the simple mechanical process is essentially a type of calculator because it will do this reliable function. And so it's here he's making a very good argument for recognizing that some simple equation likely means a simple mechanism.
These particles bouncing. Only trouble with it is that it doesn't work.
So the fact is it does work. And so it did work 300 years ago, but people said things like, well, they didn't really understand how this thing could be absorbed, okay? in terms of, a photon. So the concept of a photon was it's this little thing like a brick, and you throw it at something, and the brick either breaks or the brick sticks or the brick, and it was a little too complicated. So they were thinking that everything breaks into pieces and you get all this heat and all this other nonsense, and none of that has to happen. You can understand it as being simply this idea that it either absorbs the momentum or it reflects the momentum, and it doesn't have to be any more complicated than that.
For other reasons, every theory that you make up has to be analyzed against all the possible consequences and to see if it predicts anything else. And this predicts something else.
So it doesn't actually predict this problem, because the problem isn't a problem.
If the Earth is moving this way, more particles will hit it from the front than from the back. If you're running...
So again, says him. He just says it, but if you really think about it, it can't happen. I can't make more particles, so I can't make more particles hit me. I can only change when they hit me, not that they will hit me. If they're on this side, if there's 5 buffaloes running this way, it really doesn't matter when I hit the buffaloes. There's only 5 of them. I'm going to hit them anyway. I can wait for them to hit me. I can run into them. It's not going to make any difference, especially under this circumstance where, again, the argument is this force moves at the speed of light. So you're not going to really technically, you're talking about such tiny, minute amounts of time difference. Because it is so fast. And obviously if the thing pushing you is very, very minute, ultra mundane, very small, and it just adds a tiny bit of momentum to you, you can understand, that it's not gonna run out of energy. If it's going 3 million meters per second and you're going 3, it's like you're now going 4 or 5 meters per second and still going 3 million. So I'm just saying each buffalo that hits me, I'm not going to be able to change how hard the impact is by running into the buffalo. If the buffalo's going 3 million and I'm going 3, you can understand 3 million and 3, that's not going to make any difference, in terms of a total impact. So I can't change the impact. And all you're doing is changing when you interact with the buffaloes. And I can't change. Again, if somebody puts a 6th buffalo on that side, I'm stuck with the 6 buffaloes on that side. I can't undo that one extra until there's one extra from the other side.
In the rain, more rain hits you in the front of the face than in the back of the head.
Right, and the rain is coming down, so that's the big problem with that analogy. It's not moving, So the point is yes, if I put a bunch of dead force, and then, bowling pins, and then said, well, crash into the bowling pins. Well, yeah, obviously I'm going to grind to a halt because I had to knock down the pins. And the pins over here that I outran, so to speak, can't catch up to me, right? So the pins aren't moving, so they're not going to show up. So nothing's going to keep pushing me forward. But we're talking about a force going this way. We're not talking about a force going this way. All right. So it's an unfortunate cheat of the argument to say how much rain hits you, because the rain isn't moving towards you from both directions at the speed of light.
Because you're running into the rain. And so as the Earth is moving in this direction, it's running into the particles, rather, and running away from the ones that are chasing it from behind.
Right, so running away from the ones chasing it from behind. So just understand, it's running feeble, and they will catch up. As soon as you start slowing down, they catch up to you and push you. So you can't escape them. They will find you.
So that more particles hit it from the front than from the back.
So it doesn't happen. That's the simple argument. If they did simulate it, they'd notice that, that doesn't happen. More don't. I don't have more collisions going forward than I have from the back. It just doesn't happen. Because as soon as I stop, I'm back to the equality again, and The fact is, the only thing that made me go forward was that extra bit, and now that extra bit, okay, has been used up, and I have more force on one side behind me than I have in front of me. I used the forward force already. It stopped me. Now I'm going to have the force that catches up, and it's just as strong as it was before. None of it got used. So now it's going to essentially give me back the 1 unit of force I had lost.
And there would be a force also sideways whenever there was any motion. This sideways force would slow the Earth up in the orbit, and it certainly would not have lasted the at least 4 billion years that it has been going around the sun.
All right, so none of that happens. There's no sideways force. So that's just garbage. And obviously the sideways force is actually pushing you into the Earth. So there's a huge bias pushing you into the Earth. Anyway, so because there's more force on the outside of your orbit than there is on the inside of your orbit, as he just pointed out. So I don't know why you even bother with the side-to-side argument, because that's exactly why orbits work.
So that's the end of that theory.
So it isn't the end of the theory. It shouldn't have been the end of the theory. It's not a really valid argument. It's not, frankly, good physics, because they didn't really think about it. That I can't outrun the force, and I can't materially make more force. I can just change when I have to interact. Again, if there are 5 buffaloes and they're coming towards me, and I decide to run into them, I cannot make them into 6 buffaloes. There's still only 5, and it's always going to be 5. It doesn't matter how fast I go, and they're a mile away, and I go really fast and hit them way ahead of time. So what? And the other 5 that I outran, okay, they're still coming. They're going to still show up and push me the other way.
Well, you say that was a good one, though. It got rid of the mathematics for a while. Maybe.
Yeah, that's the tragic part, especially the convoluted, vaporous, virtual photon, dark energy, the bullshit mathematics, 1/2 mv squared mathematics, the fables, the made-up living force, woo, bullshit, all the duality equations, antimatter, all nonsense.
Maybe I can invent a better one. And maybe you can.
So that's the sad fact. Is they say this. Maybe you can. Maybe there is a better answer than our silly woo. Blah 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 blah. But we didn't think of it, so fuck you. Don't bother wasting your time, because we're really smart and you're really dumb. So it's pointless. You can't defeat our woo science.
Because nobody knows the ultimate. But up to today, from the time of Newton, no one has invented another theoretical description of the mathematical machinery behind this law.
So I just understand, it's hard for me to believe that nobody just looked at a light bulb and said, oh, that's the inverse square law. That's exactly in reverse what gravity's doing. It's just exactly the same thing. Just reverse the photons in the opposite direction, so to speak, and you have a model of gravity. So it's really, it's hard for me to take it seriously, this idea that nobody could make a counter argument. It's just you didn't want to hear it.
Which does anything else but say the same thing over again or make the mathematics harder.
So it's just, all this discount. And again, based on they say here's a critical problem, and the critical problem is based on false assumptions. That somehow, because I ran towards the buffalo, I made more buffaloes.
And at the same time doesn't produce some wrong phenomenon. They have, like this model does it, but it produces something which isn't true.
So he says it produces something that isn't true. That's the drag thing. But that's the catch is the drag is the thing that isn't true.
So there is no model of the theory of gravitation today other than the mathematical form.
Right. So I would just argue, okay, that there is now. There's not much you can say. Obviously, physics just didn't want a mechanical answer, and it just demonstrates they wanted it to remain a mystery. So it's almost like a religion. They wanted it to have some sort of air about it, of that it's out of reach, and that it isn't common. That we're not a byproduct of a simple processes. We don't want to be playing dominoes. We want to be playing chess. We don't want to be playing tic-tac-toe. We want to be playing Stratego.
If this were the only law of this character, it would be interesting and rather annoying. But what turns out to be true is that the more we investigate and the more laws we find and the deeper we penetrate nature, this disease, that every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. This is relatively simple.
So so you can see that most of their crap is really crappy mathematics. This one's really simple, and all you're saying is there a way to duplicate this mechanically? The simple truth is, yes, it was easy to duplicate mechanically, but because of your false assumption regarding how buffaloes work, you drew a wrong conclusion that it somehow won't produce what we see. And it does produce what we see.
Mathematics. It gets more and more abstruse and more difficult as mathematics. And why? I haven't the slightest idea why. It is only my purpose.
So again, and every one of these processes has these simple character features to them. So again, I could just make the simple argument that, Maxwell gave you this simple idea of charges. And, it was really easy to understand in the sense that once you establish that one's a positive, one's a negative. And then they made up this story about somehow we don't know where the magnetic monopoles are, when they're doing exactly the same thing. One of them's like a positive, one of them's like a negative. They're doing exactly the same thing. They had the likes repel, the dislikes attract. Same exact mechanism. So you're just saying it's all very simple. And again, they made up the strong force when, it's just electrons and protons elementally functioning. And if you want to get two protons really close to each other, all you do is stick an electron between the two protons, and now the protons can't see each other. You see, the electron's in the way. Obviously you get protons very close together by just sticking a charge in between them, a negative pole. Again, I just argue that they didn't, physics, people interested in physics somehow, for some reason, which I can't fathom, or find it more appealing to ponder this as a bunch of wooey mystical questions rather than to ponder it and say, what's the simplest way I can make that happen? How do I make this happen the simplest way? So I want to explain how do you get two protons really close to each other? How do I get two red magnets, south sides, really close to each other? Well, I just stick a north side between them. Problem solved. That's how, I'm just saying, it's all, this is such a failure. And the failures are always on these false axioms and false declarations. No particle model can explain. Nail in the coffin proof. They're always defending their conclusions based on scant or almost vaporous evidence. The whole existence of the positron. Same experiment. 4 people look at it. 3 people say it's a proton. 1 person says it's a positron, and all of a sudden now it's a positron.
Purpose in this lecture to tell you about this fact. In other words, it's my purpose in this lecture to explain really why I cannot satisfy you, if you do not understand mathematics too well, in trying to explain nature in any other way. It is the bird.
So again, it's a really simple process. Gravity, universal, okay, it does this really pretty simple thing, just gives things momentum, gives momentum based on mass and this simple, easy to understand inverse square law, where the force is getting thinner, all right, with distance. So not much I can say. So further. So again, I don't want to resurrect Lesage gravity. If I was to resurrect one of them, it would be Fadio, because he was the originator. Lesage just took Fadio's idea and republished it a little bit better, maybe. It was better drawings. And so, it really should be, the guy who said it first should be credited, and it's just a fact of history that he won't be, so far, and again, and it's close, but again, it's not a theory of the idea of just making a distinction between the speed of light force, the stuff photons are made out of, and the stuff that matter is made out of, because it's really trying to make matter universal. It's certainly not an ether theory, so that's the real point. And it really is saying there's these ultramundane particles. It's kind of a way of saying photon. So in so many ways it is parallel, and he thought of it in the 1600s. I mean, he did very well. In some respects, though, like I said, it's an obvious place you go mechanically. I did the same thing. I mean, I'm trying to draw it mechanically. I'm saying, how do I make moving bits create this effect? And it just sort of becomes obvious. Well, if the thing in the way is absorbing the force, then obviously the force can't get to the other side. I mean, it's sort of obvious. Anyway, so enough said, and such, and so forth and whatnot. So, till the next time, this has been, a draftphysics.com video presentation. I'd say production, but I really just don't do enough. I don't do enough production work. But anyway, till the next time. Such. Yeah, that is enough.